So moving to chapter 4 today, and it should be a pretty short lesson for today. No, I don't think Amy's going to be joining. I haven't heard anybody joining today. Yeah, I don't think anybody's going to be joining. Oh,
He does now. He's in Alabama. Oh no, I found the picture.
all right. So we'll talk today about structure of an atom, different ideas of atoms throughout the years. So we'll start with the ancient Greeks and go forward from there. So the ancient Greeks thought there were 4 elements. Did you learn about this before? What the 4 elements that they thought that existed?
Air, water, earth and fire.
That's right. Good, exactly. And that's what you see in this picture. So the Greeks thought there were just 4 elements: earth, air, fire, and water is what they thought there were. So write this down. You don't have to write down the figure 1, all that. But Aristotle was an ancient Greek, and he was the most prominent ancient Greek who advanced scientific ideas at the time. And there are others too, but he was one of the main ones. So write down this slide, not the words, but just that the Greeks thought that there were 4 elements. And they were earth, water, air, and fire. They thought we were mostly water, which makes sense. I mean, they thought life came from water, that living things arose from the water, which because they knew that animals and humans were mostly water, and they assumed that we came from the water.
So how did they explain to be burning?
Yeah, that's a good question. I'm not sure how they said that. I guess they said that you had some earth as well on you, but that you're mostly water. But there was an ancient Greek philosopher, Anaximander, and he thought we all came from fish, that he thought that all living beings arose from fish. Well, I mean, not exactly. Really? That we all came from fish? Okay.
Sorry, I apologize.
That's interesting. Did you need that one? Did you just say earth, wind, and fire? You don't need to write down anything else besides that. Another ancient Greek thinker, Democritus, he was in 460 BC. You do want to write down all of this. So I'd write down his time period that he was in, and then the 4 things that he believed about. So he was the first person to have the idea of atoms. He said that matter is composed of atoms, which move through empty space. So at the time, that was, people thought he was crazy, because Aristotle was the major thinker at the time. He was very respected. And Aristotle said that you cannot have empty space. He thought it was impossible to have empty space. Yes. Yeah, I can't. I don't know of any way. Can you not read it? Might be easier that way. Yeah, sorry. So what they said at the time is that nature abhors a vacuum, which means that they thought that you couldn't have a vacuum in nature. Aristotle thought that any empty space could not exist because matter would rush in to fill the empty space. So Democritus was not taken seriously. People didn't really respect him.
Aristotle was right to a certain extent.
I mean, he was somewhat right, but he wasn't fully right. Because we can have empty space. We do empty space.
Well, up there, but
Well, even down here.
where?
Well, I mean, the air itself is mostly, like if you were to enlarge the air molecules, so make one air molecule the size of my black filing cabinet over there, about 5 feet high. The next air molecule would be over at the stove. That's how far apart air molecules are. And the next one would be 5 stories up off the ground. So there's enormous amount of empty space in matter. Even solid things are 99.99% empty space. There's only a very little bit of matter in anything. The rest is empty space. So it doesn't seem like it, but even down here on Earth, we have a lot of empty space.
Was he the first one to discover elements, did you say?
Yeah, he didn't actually discover them. I mean, he couldn't do any experiments to prove they existed, but he was the first one to have the idea of atoms. So he was the first one to think that there are atoms. And so he looked at the ocean and he saw the sand grains on the shore. And he thought about how if you are far away, it looks like it's just one blob of sand. But up close, you can see a little bit of sand grains. Water the same way. You can have little water droplets. He thought all matter was that way.
Wait, how do you prove atoms? Like, how do
Well,
you
And that's we'll go through a few experiments they did to prove that. I don't want to go into too much right now, but the short answer is that they would shoot different kinds of particles at atoms.
I was thinking
and-
more of like a simple, robust way.
What's that?
I don't know. I was thinking
Yeah.
something like without high tech.
Hmm.
But
Yeah, I mean, well, one thing you can do is heat up water and put food dye in the water. And you can watch the food dye swirl around. And the hotter the water is, the faster the food dye moves through the water. And that's good evidence right there for atoms. Because the water itself is not moving. It's just still on the table. How is the dye moving through the water? Well, it's the atoms moving it that cause that to happen. And the higher the temperature, the faster the atoms move. And so that is evidence for atoms right there. So that's one thing you can do. Another thing you can do is what Dalton did, and we'll talk about this later on, but we saw the other day where he took 100 grams of carbon and then oxygen and made carbon monoxide. Then he doubled the oxygen, and he got carbon dioxide. That's also good evidence that atoms exist, and that they're dealing with whole number ratios that you probably have blocks of things you can't divide. He said that atoms are solid, indestructible, indivisible. And in that part, he wasn't right about, because we know that atoms do have different parts to them. That atoms are not just solid blobs of matter. That there's a nucleus, you have protons, neutrons, electrons inside the atom, and you can split the atom too. So those are things that he was not right about, but he had the right idea about atoms. Different atoms have different sizes and shapes to them. And so what he thought is that if you have something that's spicy, that the atoms were like little barbs, like little balls of spikes on them, and that's what made them spicy. He thought that like oil, it was slippery, that the atoms were like little snakes, like little like slimy things that made it slippery. So he wasn't right about that either. We now know that atoms are all circular, all spherical, but he thought they all had different shapes to make them have different properties. And so his idea was the size, the shape, and the movement of atoms determine the properties of the matter.
Well, aren't like certain atoms like have like spikes or something?
No,
Like, or maybe it's like
molecules
particles,
would. Yeah, like you could have groups of atoms together that can make up a spiky thing. But atoms on their own individually are all spheres. But yeah, they can combine and make all kinds of different shapes. Does everybody have these down? So he wasn't a true scientist. He didn't do experiments. He had nothing he could do to prove that they existed. And so for a very long time, almost 2,000 years, we really couldn't do much with his ideas because there was no evidence we could use to prove what he was saying. Aristotle, about the same time period, he said empty space cannot exist. He did not think that it was possible to have empty space. And so he rejected Democritus' idea based on that alone. He said that because you can't have empty space, you can't have atoms. Yes.
What was the last point on the board?
And he was the one who also believed that there were only 4 elements in nature: earth, fire, air, and water. He was about 384 BC to 322 BC. It's a little bit after Democritus. And he was one of the greatest philosophers and scientists of his time. And for a very long time, he was the standard for a scientist until about the 1800s, 1700s. They believed his ideas. So everybody have these down? So it wasn't for a very long time after that John Dalton was the first person to have proof for atoms' existence. He did experiments that show that they do exist. And based on his experiments, he proposed these principles. That matter is made of extremely small particles that he called atoms. Well, Democritus was the one who actually called them atoms. So atoms is from a Greek word, and they used the same word that Democritus used and he used the name that he used earlier in Greek. Just like Democritus, he believed that they were indivisible and indestructible, which again, we know that that's not true, but at the time, that's what he believed. So he was the first one to have a theory of atoms. A theory has evidence to back it up, and he was the first person to get evidence to back up his idea of atoms.
Was this was before the invention of the atomic bomb, right?
Oh yeah, well before.
So,
Atomic bomb was in 1940, so it was about 100 years after.
so, the indivisible part, was that wrong?
Yeah, that's wrong. Yeah, that's right. We can split atoms, but he didn't know about that at the time. Atoms of a given element are the same size, mass, and properties. That's not quite true either. It's mostly true, but there are, so in gold, for example, they have similar properties. Every atom in gold has similar properties and similar mass and size, but they can vary slightly in size. But he didn't know that at the time either. So those 2 points are slightly wrong, but the rest were correct. Atoms of a certain element are different from those of another element. So if you have, say, carbon and copper, they're different elements. They all have different properties. They're different sizes. They act in different ways. And his proof for their existence is that whenever he did experiments, they would always combine in whole number ratios. He always would have a 2-to-1 ratio, 3-to-2 ratio, 4-to-2 ratio. He always had ratios that were whole numbers. And that was evidence that atoms existed as indestructible balls that you could not divide into smaller pieces.
So why can't can they now make a one carbon, sorry, like 10 carbon with 15 oxygen molecules? Or does that not work?
So they could do that, yeah, because it's still a whole number ratio. It's still,
But then that could reduce 10 to 1 and 1.5.
Oh, I see. Well, it could, but you can still make a whole number ratio with it, right? You still have 10 to 15. That's still 2 whole
So
numbers.
it'd have to be big enough to be a whole number.
Yeah. Like if you were to have, say, 10.1 to 3.8 ratio, like you couldn't make that into a whole number
Then
ratio.
you could increase that substantially and make it a whole number, and that would work.
Not every ratio you can do that with. Not every ratio would turn into a whole number. Only certain ones would. Yes.
So how could they say that atoms are round if they like couldn't see them?
The atoms are what?
Like round and
Oh,
circular.
round, I see. And that's a good question. I don't know. I'm not sure why he thought that. He didn't really have, I don't know if he really, I don't know if they were just lucky to guess that. I don't know why he would have thought that at the time. I'll need to look into it and see.
What I would ask nowadays.
Well, nowadays, we have experiments, and I'll talk about that, but nowadays, we have things that can tell us more about them. And so we are definitely more confident that they are spherical. And I'll talk about that as we go through this chapter and what they've done to see atoms or have an idea what they look like. But Dalton at the time, he couldn't see them. He had nothing that he could use to even attempt to see them. So I don't know why he would think they were spherical. I'll look that up and see. I don't know if he just looked down to space, he saw the planets were round, he thought maybe that's why they were. I'll see.
And also round atoms can just create like any shape.
What do you mean?
So if they like combine together to form like different molecules, like those molecules have different shapes, right?
Oh, yes. Mhm.
And they are not always like round or circular. They can have like.
Right, they can be different shapes. That's correct.
So
Yeah.
if they're round, how can they make like, I don't know, just like rectangles? Like how?
Well, it wouldn't be a true rectangle.
Oh,
It would be, it's now it can appear to us like like this
What-
looks like a true
What's the,
rectangle. If you were to zoom in, you would see it's not a true
okay.
rectangle. But it's close because they're so small. It looks to us like it is.
What is the crystal that's like square, like it's?
Well, there's a few that are square. I mean halite.
I don't know.
That's one of those square.
How square would that be?
Well, I mean,
If you zoomed in.
maybe very square. It's just that because atoms are very small, but it still wouldn't be perfectly square because you do have they're round, and so you definitely would have an edge that's not perfectly square.
Alright.
So Dalton's idea is this. Did I go through everything? No, I didn't. Sorry, let's go back to this for a second. So different atoms combine in simple whole number ratios to form compounds. In the last bullet point here, in a chemical reaction, atoms are separated, combined, or rearranged. So they're never destroyed, never created. They're only recombined, broken apart, recombined in reactions. So Dalton thought this, that in a reaction, this has gold and purple atoms. And then when you combine those two together, they then combine. You can see right here that you have two purples combining to one gold. That's how you get a different compound. But you don't lose atoms, you don't make atoms, you just take what you already have been given, in this case 4 gold and 8 purple, and you combine them in different ways. Yeah, that'd be good if you could. You don't have to write down the words, but writing down, like drawing the dots, that would be good to understand what's happening here. But that was his idea of reactions, that you just take samples of atoms you already have been given and recombine them in different ways to create different new compounds. All his experiments prove this to be true. He could take some hydrogen and double the amount of oxygen present, he would get H2O. If he had equal amounts of hydrogen and oxygen, he would get H2O2. And that was good evidence to him that atoms existed.
But not every ratio can make an element.
That's right. They're not always stable. So you can't, yeah, that's right.
Is that how they make atomic bombs? Do they make unstable ratios?
Not exactly, because usually when we say unstable, it might be explosive, but not always explosive.
Could they do that though?
So what they do instead, because it really wouldn't be helpful to do that, if they're very unstable, they usually just don't last for too long and they make stable compounds very fast. And you don't always see fire or explosions with that. In atomic bombs, what they do is they make atoms split apart. And when they split apart, energy that's released is enormous. And that's the idea behind atomic bombs, is to split atoms. It's not chemical, it's a nuclear
How many
reaction.
Atoms do they have to split to make it?
Oh, no, I mean, trillions and trillions, I'm sure.
Uh,
Now, at the beginning, you only have to split one, but that gives you a chain reaction to split the other ones.
So they have to split a substantial amount.
Well, you can just split one to start with, and that one can then,
Well,
Like a
yeah,
chain-
but
like
in
a
the
domino.
end,
oh yeah, in the
substantial
end, you're gonna
amount
have a
has to be-
lot splitting, yeah, that's right.
Um,
Yeah, that's right, you need a lot.
What happened if just one split?
I mean, you wouldn't really
Would it
see
even-
anything. You wouldn't be aware of it. Like it'd be so tiny, you wouldn't even know that it happened. Now, the amount in this pin would be enough to have a nuclear bomb. I mean, so this would be, all the atoms split in this pin, you could have a pretty good nuclear bomb.
So when
So
they
that's not a
split-
lot that you need.
When they say they split atoms, do they mean just the uranium atoms?
Mhm.
Or do they mean all the atoms in the surrounding?
No, just the uranium.
And why don't the atoms in the surrounding area split too?
Because they're not big enough. Usually only big atoms can split. And the ones that are smaller aren't very easily
So
split.
do they change the elements in the area around sometimes by adding the atoms?
Oh, I mean, not usually, but oh yeah, a few might change. Yeah, you might have a few different elements.
People-
I mean, but there wouldn't be a lot of that. So Dalton, as I mentioned, he was right about a lot of things, but there are things that we learned in the next century that were not correct. The two big things that we learned is that you can divide atoms in certain cases. In nuclear reactions, you can split atoms. In everyday life, though, we don't split atoms. You know, chemical reactions in the laboratory, we don't split atoms. And so in my class, we can't split atoms. We don't have the equipment to split atoms. So it's not a very common thing, but it does happen. And not all atoms of a certain element are identical. So Dalton thought they were, but we now know that if in a given element, some atoms are bigger than others, they're still all the same kind of atom. You know, if you have a sample of carbon, they're all carbon atoms, but they don't weigh the same amount within the carbon sample.
Wait, so atoms are divisible? Does that mean they can break like down?
That's right.
I thought, wait, so then, what about elements?
Yeah, that's elements are the same kind of atom. So an element would just be the same kind of atom. So elements are atoms.
So didn't we just then that like elements couldn't be broken down or something?
Well, chemically they cannot. So you can't take a bar of gold and chemically break down the atoms. And you can do it with nuclear reaction, but through chemical reaction you cannot. So that's what they meant. You cannot chemically break apart the bar of gold into atoms that are smaller than the gold.
Wait, so does that mean like one atom can be broken down?
In certain cases it can, just not chemically. But in a nuclear reaction it can. So only a certain situation can it break down. In normal everyday situations it cannot break down.
So atomic reactions are nuclear fission, right?
Yes.
So if we came up with something that could make nuclear fusion, would that be perfectly clean energy?
Yeah, because, well, the exhaust would be water. You would just have water created.
Oh.
It would be, so yeah, it would be very efficient. You would just, it'd be,
And if we did that, could we then take the reactant or the thing produced and use it in nuclear fusion and turn it right back into energy?
what do you mean?
So if we did, so if we use, the scientists use nuclear fusion to turn energy from the sun into an atom, or into multiple atoms, and then use those atoms in the nuclear.
Well,
fission.
nuclear fusion, what you do is you take hydrogen and you combine it to make helium. Like you would smash hydrogen atoms to make helium atoms.
Wait, then what's getting energy into mass?
The energy into mass, we don't have a way to do that yet, but that wouldn't be nuclear fusion. Nuclear
Oh.
fusion is taking two atoms and combining them to make a bigger atom.
Sweet.
We don't know how to do that yet.
If scientists did figure out how to make energy into mass, would that be perfectly clean energy?
Yeah, it would. Yeah.